Yeah? Hello? 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 Okay. What
It's not
is...
focusing. Oh, whoa, what happened to it?
Did you
Wasn't
close it?
focusing.
Oh, yeah, it doesn't show them now. So,
Okay. Hello. Okay. It's not like auto-focusing.
you can, hold on, go out, go to the controls. Then check and uncheck this focus auto. No, uncheck that and check it again.
Okay, while we're at it, let's do the manual mode, which it was not staying in. How do you get out of the, just Alt-Tab, is it a toggle?
Yeah, no, Alt-Tab switches between windows.
No, but if I wanted a... Okay, so for example, it's supposed to autofocus now that I've changed the exposure.
Let's see, oops. Let's disable that guy. Oh, that's much better. You have to disable focus auto in order to, and then you can use that to make it actually try and focus, and that seems to work.
Okay. Well, that's better. Now
Okay.
to get out of this guy?
No, just
once I
you have to
click
leave this.
capture-
You have to leave this open. This is these two are part of the same program.
Oh, but once I click capture, it'll just go away?
No, it'll stay, and you can. But then you can switch. Just leave it. Just hit Just try and see just keep this in view and see if you
Okay, I'll
if
just
the
make
exposure
sure
is
I hit
right.
capture.
Okay, sounds good.
Fine.
Well, can you? Okay. It's also got some zoom control there. I'm not sure if you want to play with that. We can try.
You can see the board.
Yeah, no, that's bad. Okay, that should work.
Is that cool font size wise for you guys in the back? Yeah? Good. Ten after, right? Yeah. Okay. Right. Oops. Aren't you? No problem. I'm not sure. I didn't find the lid upstairs. Okay. All right. So that puts us at 10 after. Welcome to lecture number 4 for high-performance scientific computing. We'll call this one OpenCL, this time for real, unlike last time. And, well, let's start out. How are you guys? How are you feeling? Any comments, questions, concerns? You want homework? You want more, yet more homework? You'll be very happy. Okay. Right. So we'll do a new thing today. Call that tool of the day, and I'll briefly tell you how to use make. You've probably seen me use it eventually, and today you'll learn how to do that yourself. We'll briefly recap what we said about why GPUs as chips make sense and why people build them, but we've been through that last time, so we'll go quickly, and then I'll actually show you how to program them. Okay, let's get started. But first, so homework 1, sorry, we're still a little bit behind. We just hired a grader, and it'll be graded by the weekend, promise. Homework 2, due today. If you need emergency extensions, ask now. And homework 3 will be out after this class. I'll post it. This will be programming GPUs. Then an accident to report. So during the first class, I said sign up on these sign-up sheets and we'll sign you up for a high-performance computing account with NYU. Turns out, not so simple. I sent them the big list of names, and they were, thank you very much, please send your students to this convenient web address to sign up themselves. So if you haven't seen the email on the mailing list, there's a link in there, and you have to go there and fill out your net ID and stuff. Sorry about that. That was a change policy from last time around. Then, just to provide some closure there, any more OpenMP questions? Nope. And I want to share one OpenMP anecdote that Alex had in office hours. So the issue was that he was using a Mac. I'm getting your first name right?
Yes.
Right, cool. He's using a Mac, and the Mac has GCC 4.4, which doesn't do atomic operations like I've taught them to. So, well, we got ourselves in this mode of thinking, you know what, let's try and fake atomic operations by using a critical section. It's sort of the same, right? You know, sort of the other thread can't get in between. So let's try that, right? And you get the same structure that we had last time. So basically, well, let's think what the atomic structure was supposed to look like. You grab the lock, and then you do stuff, and then you release the lock afterward. Right. So that works by, well, usually you'd say pragma omp atomic capture. Capture. You'd read the previous value of the lock, that's called that L, into a temporary variable, and then you'd assign the value, let me be more careful here, 1 to that lock by ways of a bitwise OR. Right. And then sometime later, so you put a loop around that to see if you've succeeded, and if you have, then you do your stuff, and then sometime later you assign L equals 0 to release the lock again, right? That was the story. Okay, so now you put yourself into our shoes. We're like, you know what? No, we don't have that. We'll make this a critical section instead. What could go wrong? What did go wrong? I know you know. Anybody have a suggestion? So this highlights a key difference between atomic operations and critical sections, right? If one doesn't quite behave like the other. Can you guys all see? I can try and shuffle these blackboards around. Did I just make the video unhappy? Okay. Right. So, what's the problem? What has become interruptible that used to not be? What's the scenario? So the problem that we observed was a deadlock. How did that happen? It must come from this guy being interruptible in a way that it wasn't before, right? So an atomic operation makes this whole entire thing up there interruptible, uninterruptible. Is that interruptible now? Perhaps by a conflicting right?
Yes.
Right. Can you explain?
So one thread is in there,
Uh-huh.
and no other threads can be never. Another thread can do something set L to 0.
Right. So first guy reads L, based on that read, concludes, hey, hey, I didn't get the lock. Then the other thread assigns L to 0. Then this guy comes back, assigns it back to 1, but still believes, hey, I didn't get the lock. Or the other guy also believes he doesn't have the lock, nobody has the lock, and you have your deadlock. When we figured that out, we felt pretty damn clever. Anyway, I thought I'd share that because I thought it was cute. Any questions on that? Does not seem to be the case. Okay, let's move on. Yes, I guess by now you're sort of used to it. I'm harping on that final project. So, please try thinking about it. I've put some examples from last year here. So somebody wrote a GPU parallel finite difference solver that could sort of do flexible geometry. Somebody, you can read that yourself. Did some password cracking, or somebody wrote a vortex method that's some computational fluid dynamics thing. Somebody did cool geometry processing that was fun to look at during the demo. Stuff like that. This and I think that actually supported these guys' PhD or master's thesis research. So, and we're also encouraging you guys to work in groups. So if you have an idea for a project but you're looking for, like, it feels a little bit too big to attack on your own, just look for a buddy. We have this mailing list. Just ask, that's what I'm trying to do, and then you'll get applications, and you get to interview applicants. Right, and also while we're teaching this class with kind of a numerical bias, obviously you guys can do non-numerical stuff too. If you want to do GPU sorting or something like that, that's perfectly fine. If you have more of a CS bias yourself, that is okay. So, any questions? And if you have, come see us, and even if you have just a half-baked idea on the project, we'd love to hear it, and we can give you feedback. I hope that sort of gives you an idea of what we're looking at. Any questions here? No? Okay. Right. So, order of business, thing number 1, tool of the day. Make. What exactly does make do? Well, so the way that we've set up the homework so far, I bet you guys are all mighty fed up with typing compilation commands. You're like, okay, cc vec add.c. Oh, it doesn't work. Okay, let me adapt that. std equal GNU 99. Still doesn't work. So it's all pretty repetitive. Okay, still missing something. Right, and you know the story, right? It's just really annoying. The gods of computer science have created make to fix exactly that. So, and you control make by something called a make file. And it's important, it's sort of important, that you spell that with a capital M, or that at least that's a convention. And then what happens? Well, so the idea is somehow stuff needs to get compiled. And the thing that make brings to the table is it allows you to describe dependencies. As in, you have your source code, and when your source code changes, whatever compiled stuff comes from that machine code, that needs to be updated. And then you have some commands that describe how that happens. So let me describe that. So I just put together this line to compile my vector add, and that depends on vec add .c. And in order to compile it, I had to type gcc -std equals GNU 99 -l OpenCL. You remember what else I needed? -lrt, I think. cl helper.c, and obviously also vec add.c. Okay. Then, so this is the same setup as we've been using. The editor is the thing with the dark background, and the shell is the thing with the light background. Can you all see the screen like that? Okay, so then. Okay, actually, then you know what? Maybe we'll just, yes. Maybe you guys can tell the editor just like that too. Oh yeah. If that's better for the video, then let's keep it like that. Okay, right. Okay, so here's the make file thing I've written. which depends on vec add.c, and then I can say make vec add, which tells make to make whatever I've told you how to make vec dash add, just do that, and it did. It just ran that same command that I told it. Okay, what do you think is going to happen when I run it again? Huh? Nothing. Well, I agree with you that nothing should have happened. Why did it do that? Such is the nature of demos. Is the date off? Not sure. Well, okay. What did I screw up? Huh? I didn't quite hear what you said. Huh? Oh, it makes a.l. Yes. Okay. Sorry. Yes. Good point. Right. So when I actually have it make the correct output, I think it's fine without the space, I believe. Okay. Now the right thing happens. It says vec add is up to date, so it looked at all the files that I said it depended on, and if they haven't changed, then it doesn't remake it. So if I then go in and edit this C file, I'll just add a blank line and remake, then it gets recompiled, and after that it's up to date again. Okay, so that's lovely, but that's just a very simple case. So in principle, another thing that you could say belongs here is this other C file, right? At that point, you start looking at that and thinking, okay, that starts to be a lot of redundant information. So make actually provides some ways to avoid all that redundant information, and there's something that you can say that says all the things that I depend on. So instead of all the C files that I wanted to compile, I can say $ and caret, and the caret in the sense of point up, like all the stuff that you can find up there, and just stick that onto the command line, right? Okay. That hasn't really changed. Then a quick shortcut to update a file without really updating it. So suppose I had changed the CL helper, then my updated command gets run. So that's lovely. Another thing that I can do is replace this guy here. So in terms of terminology, the thing on the left here is called the target. That's the target that we're making, and the stuff on the right is called the dependencies. So if we can specify all the dependencies with some $ something rather, then there's probably also a way to specify the target. That's a little bit less obvious. That's $ and at. It had to be some nonsense like that, right? So let me this time touch vec add.c and make, and it does the right thing. So there you see it plugged in vec-add. Right. Okay. And then you can just fill this make file with a lot of rules like that. Another thing that you probably want is, well, it's possible that these things screw up unless you're very, very careful. Can you tell me one thing that this make file, for instance, gets wrong? What kind of change should lead to an update but doesn't? And so the key bit of information is that there's a header file. Why is that potentially bad? A header file for the CL helper.c. Right. If the header file gets changed, then this won't cause this won't cause make to rebuild it unless I would tell it, okay, CL helper dot h is also a dependency. But that gets sort of cumbersome, and eventually you'll screw up and just want to blow everything away and start from scratch. So a conventional way of doing that is to have a rule that's called clean, and that just removes all the stuff that you've built. So then you can say make clean, and that removes what you've built, and then you can say make. Make automatically picks the first target from the make file and makes that if you didn't tell it otherwise. So that is a quick, that's a shortcut to build everything. Another neat trick is if you have multiple executables like you might. So in this case, I happen to know that there's the solution to my demo stuff somewhere. Suppose I want to build that too. Suppose I want to build everything. How would I do that? Got any suggestions? Make all, okay. Let's see. Make all. No target to make, no rule to make all. Okay, how do I fix that? Okay, I'll make a target all. And what do I put back here? Right, I'll put vec add and vec add solution. And then if I say make or make all, then it built that, fine. If I rebuild from scratch, so make clean, and then it builds everything automatically. Okay, one last thing. So now I've got duplicated information again, namely the name of all my executables. Here's vec add and here's vec add solution, and I have the same thing over here. In order to make just one place where I can put this information, I can also have a variable, say call that executables, and then equal these guys, and I can recall the variable name like that, and like that down here. Then there's only one place where I have this information, so it's easier to keep updated. All right, that's about all I wanted to tell you about make, and we'll use that during our demos today. Make clean, and make works the same way it does. Any questions on make? Nope. Great. Okay, so make tracks dependencies and can run commands based on whether it thinks if stuff is up to date. How does it tell if stuff is up to date? Well, it just looks at the modification date of the file. That's all. It doesn't. It's no smarter than that. Okay, great. So let's go back to the lecture. Right. Kind of a switch of topic. Back to GPUs. Where were we? Well, I was trying to get you really, really depressed looking at this picture. Why? Anyone remember why this is depressing? Don't depress me. Yes. Yeah.
Because basically, the large majority of the things on there are just put in to make sure that the CPU has stuff in its scheduler, or it has as much stuff in its scheduler as possible.
Right. Exactly. Like the thing that does work here. All this other stuff, not really. I mean, not doing useful work. Just keeping this guy fed, right? And the problem is memory is slow, so if stuff takes a long time to come back from memory, then you have to be careful and predict and get stuff beforehand and try and do stuff out of order. So that here, if the expansion of that is reorder buffer, that's how you can tell that this is an out of order CPU. So it's just a big old idiotic complicated thing. And really, it's also a single-threaded thing. It's not a parallel thing, right? It's not very good at doing parallel stuff. It's just meant to keep this one single thing fast. But if you have a parallel workload, just you care about throughput, stuff that goes through a machine, then you're not too worried about one guy stalling because he runs out of work. So you can just switch to something else parallel that you might have sitting around. Right. So junk, 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 and more junk. Get rid of it. That means we've suddenly got way more space on the die, and we can put way more execution cores. And that, for example, would give us 16 independent cores, and thereby we could execute 16 independent things. Now, if you look at scientific computing codes, like say a code that adds two vectors together, it's not just that everybody does something wildly different. It's mostly everybody just adds these two vectors, so everybody does the same thing. So being able to control all these guys independently, not all that necessary. Maybe we can sacrifice a bit of control for more computational power. So for to each of these controllers, we'll just attach a few more execution units. And that gives us a single instruction multiple data machine like that. And as we discovered last time, we can't just add more execution units. We also need to add a little bit more on-chip memory for those to give those data to work. Right. So that gives us that chip, and all of a sudden, instead of one thing, we're able to do, in this example, 128 things with the same chip area, and no other loss if our workload is just that parallel. That's lovely. So that's great. If indeed everybody in this group does the same thing, right? That's sort of what that's predicated on. Except that doesn't always happen, right? Because as soon as you write an if in your program, it could happen that half these guys take one branch, the then branch, and half of the other guys take the else branch, right? So what would happen then? How long would that whole if-else thing take to execute? Any clues? So here, okay, here we've got some I don't know exactly what this does. So it has an if in there if x is greater than 0. And here comes our SIMD vector in with all its data. And everybody is executing the same stuff. And they get to this branch. And only for a bunch of these guys, this evaluates to true. And for a bunch of others, it evaluates to false. Oops. Now what? I mean, we built the machine so that it's good at doing the same thing for everybody. But if we want to follow this program, can't do that. What do we do? Suggestions? I'll give you a word. Mask out. Does that help? As in, we'll have everybody go through both branches here, but only execute if we're in the right branch. As in, so suppose this guy here evaluated to true, so he needs to take this branch. So we'll execute for him here, but we won't execute for him down there. So like that, right? So the guys that evaluated to false, they just have to be along for the ride, but they're not doing useful work. And the same thing happens in the else branch for the other guys, right? So that's the downside. We traded some control granularity for width of processing. That's how we pay for that. That's just a natural thing. So that's something that we might need to keep in mind. But in terms of the meaning of our programs, that's perfectly preserved. This is just an execution speed thing that I thought was useful to see at an early stage, just because that's how we design the machine. Right. So in this case, if we have a bunch of nested ifs, right, then so that everybody executes on their own, the worst thing that could happen is that everybody does their own thing, and we get 1/8 the performance, or It turns out on actual machines, the width of this is actually 32. So it's not hard to see that you could easily lose, almost all your performance out. Yeah? Absolutely, yeah, no. Just one is not going to do it. But consider this. If you have a loop, that's an if statement at the end of every loop, right? So the first guy decides, okay, I need to exit the loop. Second guy decides, so that could whittle down the number of people that stay in the loop. So it would be useful to try and make sure as much as possible that everybody takes the same branch. Yeah?
Also possible, like, that you could just set it and have everybody do all the processes, and then as it's coming back, it does the processes. It basically says, like, you do need two false statements. The first element is a true false. The second element is a y1, which is the processing element. The third element is the reflection one. Fourth element is
that might be in this specific case that might work, but I don't like that strategy particularly, just because it relies on two things. The first thing it relies on is that whatever gets done in here can be undone, and that's not always the case, right? You'd have to look at it in more detail and like undo the stuff that happened. So that's not very practical. And the other thing is, well, you put this onto a GPU-like machine because there is so much of it that you couldn't afford to do it on your CPU in the first place. So doing something even more complicated to roll part of that work back is not going to make sense, right? Just from a volume of data sense.
well, in this particular case, you're just literally burning time doing exits where you're doing no calculations, right?
Sure, but
In theory, you could do it. You're basically trading memory for
well, no. So this is a chip design trade-off. You're trading area that's spent for individual control for being able to control each of these guys individually. You can still fake it and do that, and that's not a complete disaster. So if you're losing 1/8 of the performance, sounds disastrous. The truth is, most of what these things do is wait for memory anyhow. So in reality, you're likely never going to see that factor of an 8, and that doesn't pay for the expensive thing that you suggested. I just thought it would be useful to understand how the machine ticks on the inside. Okay, and we'll cover in detail how fast these guys go under what circumstances. For now, I'm just more worried about telling you what the meaning of stuff is. And one key to understanding the meaning is knowing that there's this hierarchy of we have cores, and then each core individually is split up in a vector like that. Questions? Okay. Right. And the other thing I want to convince you of is that this is not just some joke. Like GPUs, okay, somebody went to Best Buy and bought a box that has, big alien monsters on it. And, whatever teenager might be the core audience of that. No. That would be benign if that was some fringe phenomenon. The problem is making conventional CPU chips bigger and more powerful is just not going to work. So GPUs are especially useful as a cartoon of what all processors are going to look like at some point. So it's a grim preview of things to come. What is this nightmare limit? The nightmare limit, well, what's easy is just planting infinitely many processing cores on each chip, and then saying, okay, it's also easy to equip each chip with infinite vector width, right? So the latest chips that come out of, say, NVIDIA or AMD easily have thousands of floating point units on them. And the only challenge is really how do you control all this stuff? And that's what this next part is about, where we talk about how to program. And as you saw, like the main selling point of these things is that there's lots of bandwidth to be had, compute bandwidth and memory bandwidth. But you only get that if in some sense the work that you fire at the machine is homogeneous, as in everybody is doing the same thing. Right. And you might think, but that's a CPU, right? Intel Ivy Bridge came out this year. That's true. There's 1, 2, 3, 4 cores. That bit of it is actually a GPU. And it's programmed in the same way that we're going to cover. So I'm not, what this slide is supposed to mean, I'm not making this up. And people keep designing these chips and they keep getting bigger and better, and it's just not going to go away. If you have a computation that cares about throughput, this is one good tool to have in your tools. Right. So that leaves the question: how the hell are we going to program these things? Right. In terms of names, well, the thing that we're going to use to program them is called OpenCL. It's Open Compute Language. Computing language is an open, royalty-free standard for general-purpose parallel programming across CPUs, GPUs, and other processors, and the kitchen sink too. Right. Why that? Well, there are mainly two interfaces to be had. You might have heard of CUDA, and you might have heard of OpenCL. The main distinction between the two is, well, OpenCL can run on CPUs and GPUs, so it's also a valid way of programming just regular processors, CPUs, and it runs on GPUs of multiple vendors, and it comes with just-in-time compilation. What on earth does that mean? That means your stuff doesn't have to be compiled up front; it gets compiled at runtime, and that you might not see the advantage of that just yet, but you will at some point. And it comes as a library. So you've seen me type -L OpenCL. That means you link to some host side library, and then there's a programming language that's like C on the side of the device. Right. I'm gonna have to fire a little bit more vocabulary at you. So the CPU, as in the thing that you're used to programming, we'll call the host. And the stuff that we're programming this way is called a compute device. So this could be a GPU or a CPU, and it could very well be that the CPU is just talking to itself that way, as in this and that could actually be the same thing. It's just programming itself with this interface. Another specific thing is that each compute device comes with its own memory. And that'll have a very direct consequence when you program. Namely, you've got data over here. Well, that's nice, son. The compute device can't do anything with it. So you'll have to transfer it over here before you can do anything. And then when you're done computing over here, you have to transfer it back. That's obviously a cost, but for many things, that cost is actually worth it. So that tells you something about how fast these things can actually go. Right. Then, more words, okay. So these things come grouped into platforms. It's one of these CS words that means everything and nothing. And say, you'll see this when we start programming in like 5 minutes. That say all the stuff by NVIDIA is grouped in the NVIDIA platform, and all the stuff from AMD is grouped in the AMD platform, and then all the GPUs attached to that are in there. Right. And just to give you an idea, well, one of these compute devices is like a chip, right? Something that has a memory interface because memory was attached to it. Then with these guys always are somehow subdivided into these cores, and then each core has a bunch of vector links, right? So that okay, we can duplicate cores, and then we partition further into vector lanes. That's deeply ingrained in this OpenCL, right? And we'll program over here with this library, and over here with this device language that fortunately is just C. Okay, if you're in CS and UML makes you happy, that's OpenCL in one slide. So that's just as a preview all the words that are in the standard. for now, you don't need to understand too much of that. So you've seen platform and device. There's going to probably be programs, kernels, context, mem objects, buffers, images, samplers, events, and command keys. Fantastic. We'll get to each of those when we need them, but no sooner. And this, if you go back to the slide in the future, this tells you, okay, to each platform there can be multiple devices. To every device there can be multiple programs, and blah. You can read this on your own. Right. Okay. Right. So next question. We have a chip that looks like that, right? We have a bunch of cores, and each core has a bunch of vectors. How do we make a programming model for that? Does it make sense to expose how many of each there are? Does it make sense to sort of tell the programmer, okay, this is how many cores you have, and then just like OpenMP, say, okay, you get 4 threads because there are 4 cores? Or let me ask that differently. Why doesn't that make sense? Huh? Right. That's one good reason. Everybody's doing mostly the same. And the other good reason is, well, it's also tremendously variable information, right? So if you look at the slide there, one of these things comes out from each manufacturer about once every 1.5 years. So by the time you're done writing code for one chip, another comes out where that number has changed. So it doesn't make sense to bake that information into the programming model. And really, who cares? Right? And honestly, the same thing applies to the number of vector lanes too, right? It's not really information that you care deeply about. You sort of know how the parallelism works at that level, but you don't really want to know how many there are. So what we're gonna pretend instead is that there are infinitely many cores and infinitely many vector lanes. That's based on this consideration, namely, if you've got a sequential program, how easy is it to turn that into a parallel program? Well, you've suffered with OpenMP, right? It's not always that easy. But if you have a parallel program and want to turn that into a sequential program, is that difficult? Not really, right? Because if you know that there's a bunch of parallel stuff, since you have no guarantees on who gets executed when, you might as well just execute that stuff in sequence instead of in parallel. So it's easy to turn a parallel program into a sequential program, but the other way around is hard. So the basic idea is, well, let's just throw as much parallelism at the wall and see how much sticks. As much as we can, and then it's up to the hardware and the software to figure out how much to actually run in parallel. Right. So on the programming side, that ends up looking like this. And there's more terminology. So this is the hardware. That's the software representation of it. And what you ask for is a grid. Now, why is this a grid? Well, these guys were called GPUs for a reason. Well, they do stuff with graphics. Graphics is usually 2-dimensional, so people do stuff with images. Conveniently, you'll be doing stuff with images in the homework too. So, but the two-dimensional nature, say, of this grid is completely artificial. I mean, this is core number 0, core number 1, core number 2, core number 3, core number 4, core number 5. There's no two-dimensionality here. It's just a convenience that the device offers for you. If you have something that's sort of two-dimensional, where you like the number of threads that you want to launch can be described in some conveniently in some two-dimensional manner, then you can use that. You can just as well have a one-dimensional grid, right? So you say, okay, I have this many parallel things that are a one-dimensional grid, so to speak, and then let that thing figure out how to deal with it. Right. So, and you see that there are some lines here that are thin and some lines that are thick. And that's how the second level of the parallelism shows back up in the programming model. So the next subdivision from a grid is called a work group. And you explicitly specify the size of a work group as well. And a work group says how many of these individual work items are going to end up on one core. So a group corresponds to one of these cores. Right, and each individual thing here is a work item. So now, that begs the question, if that's what we have to work with from the software side, how would we stick that onto the hardware? Huh? Well, right, but I mean, somehow we made a promise that only stuff from this box goes to the first core. Only stuff from that box goes to the second core. So that's not it's a good start, but it's not quite everything. But I mean that's probably a good start by saying, okay, let's take this work group and stick it onto core number 0. Let's take the first 3 and stick them onto the first 3 cores. And once we're done, once we've assigned stuff to each of our cores, then we've still got more work groups left over, and that's okay. We'll just get to those later. And then within each of these work groups, we'll do exactly the same thing, right? So you see here that there's quite a bunch of these work items in that work group. And well, we've only in this example got 8 vector lengths. So fine, take the first 8 on each of these cores and execute them. Once they're done, take the next 8. Once they're done, take the next 8. Once they're done, take the next 8. So really the idea is this funny grid thing just provides a pool of parallelism that the device can draw from. And the actual 2D or 3D structure of this doesn't quite matter. So in the performance part, we'll get to where there's one thing where something from the lower level shows through, in the sense that that say these guys execute together, and there's some way to use that fact. But in terms of the meaning of your program, you could which of the XYZ axes you pick for what completely does not matter. Right? So the 2D thing, as I said, is really just a convenience for you that you can take or leave as you please. And so within certain limits, you can just pick the size of this grid in a way that's convenient for your problem. Right. Okay, and then once you're done, then you take the last 3 and assign them over. Okay, so let's move closer to actually programming. So what happens is you will end up launching one of these kernel things, which is what a function running on a compute device is called. And within that kernel, well, that kernel gets executed like we've just seen. Within that kernel, you're able to inquire where in the grid you live. And you can do that using these functions here. So perhaps the easiest one is asking for your global ID. So let's talk about this guy. So global ID is the index. Say, if you pass a 0, then that's along the x-axis. If you pass a 1, that's along the y-axis. Is the index of this guy relative to the origin of the grid. And the local ID is relative to the origin of its own group. And the group ID is the number of the group in group units relative to the origin of the grid. So let's practice. Here's the little highlighted guy. What's his local ID? LID of 0. 5, 6? Let's build a consensus. So it's relative to this thing here, and like everything in C, it's numbered starting at 0, right? So that's 0, 1, 2, 3, 4. Makes sense? Along the x-axis. So local ID of 0 is 4. Okay? Local ID of 1 is 1. Right. Okay? What's the group ID? Group ID of 0 is 7, 3, 15. What do we count? Big boxes, right? So this is big box number 0 along the x-axis. So 0, 1, 2, 3. Okay. And group ID of 1 is easy enough, 1. Okay. Global ID of 0. Oh no, we have to do arithmetic. I heard somebody answered, I didn't hear you. 25. To be honest with you, I kind of stink at arithmetic. Can you give me a formula? So, okay, these guys are 7 wide, right? 1, 2, 3, 4, 5, 6, 7. So, you said 25, written as 3, my group ID, times 7 plus 4. Does that work out? 3 times 7 is 21 plus 4 is 25. I agree. Okay, on this end, global ID of 1 is 1 times 7 plus 1, which is 8. All right. Any questions on that? Nope. Clear as glass? I'm glad. Okay, and like I said, 1, 2, 3 dimensional. You can choose yourself. Okay, let's see how that works in practice. All right, what do we got? So I've prepared a little something. What's going on here? Well, it's the same. So actually, what I'm doing is warming over the vector addition demo from the first class, because that was kind of rushed and it didn't end up working on the GPU. I thought it was worth going over that again. Right, especially now that you have a bit more of an understanding of what's going on. Right, so we ask for the length of our vector and the number of trips. Then comes terminology land. So we'll need a context. That's just like, that's the big thing in the middle in that diagram that everything was attached to. So you need a context to do everything. Then apparently we also need a queue, and that you can sort of imagine what a queue is supposed to do. So let's leave it at that. We'll go into that in a little bit more detail. Then comes a helper function in a library of helpers that I provide for you. You can find that on the web. It says, okay, create context on a device made by Intel, and I don't care what that device is called, and I would like that returned, that context and a matching queue returned in these two variables. Well, let me see. So actually, I would like to know what I have available on this machine, right? So I edit my make file, and let me see. There is some code that I've got here, print devices.c, that tells me that. Whoops. Print devices, and that is print devices.c. And I add that to my executables variable, print devices. And I can hopefully run that now. Aha! So we've got quite the menu. What do we have? Well, apparently we can talk to our CPU, which in this case is some Xeon, through an implementation from Intel and through an implementation from AMD. And then there are 4 GPUs attached to this machine, all made by NVIDIA. So whatever these model names mean, higher numbers are better. How did you possibly guess? Right. Okay. So and just to have the have all the vocabulary make sense, right? Whoever made the implementation, that determines what the platform is. So there's an AMD platform, and then there's a device attached to that. Then there's an NVIDIA platform, and then there are a bunch of devices attached to that. Then there's an Intel platform, then there's another device attached to that. Make sense? Right. Okay. So there. So we, in our vector addition thing, we said, well, we would like the platform made by Intel, pretty please, and whatever device you can find in there. Let's run on that. Okay. Then we ask, okay, read a file. That's another helper function that I've provided, and unsurprisingly, it opens that file, reads it into a string, and gives it back. So let's take a look at what that thing does. Vec add dot, whoops, no, that's already open. Vec add dot cl. Okay, unsurprisingly, that's just our idiotic vector addition, right? Just some for loop. So this is nothing surprising if you've seen C before, except there's a bunch of gunk that we don't quite understand. There's something that says underscore underscore kernel, so that function must be called a kernel, and then there's with that pointer it says global, so that means we don't know what that means yet, but that means that the memory behind that pointer is in global memory. Let's just accept that as a fact. That points to global memory. Fantastic. Okay, and otherwise we're just passing the number of entries, and we can run our for loop, and that's really the entire story. Cool. Okay. Then what do we do next? Well, we make a kernel from string, so you can recognize stuff that has to do with OpenCL by the CL underscore prefix. So we get a kernel from the string, right? And this is the text that we just read from this file. So this is where the just-in-time compilation comes in, right? So there, behind this function call, there's actually a C compiler that builds this thing, and then we can later run it. Right. Okay. So we get rid of that string, and we move on. Right. So if we want to add 2 vectors, we need that data. So we first allocate it on the CPU, as in on the host now, right? And fill that with I and 2i. And then we do the same thing over again on the device. Okay? So allocated memory apparently is called a buffer. So CL create buffer. A bunch of gunk. Apparently here we pass the size in bytes. So size of double times n, size of double times n. And then apparently there's some error to check there too. Right, so we do that for buff A, buff B, and buff C. And that's the consequence of what I said. Each compute device comes with its own memory, so we have to allocate over there and then transfer. So the thing that's still missing is the transfer. That comes next, and that's these 2 guys. So CLNQ write buffer. Lots of words. Write buffer is really the key word, right? We're going to take stuff from the host, namely n times size of double bytes, pointed to by A, and stick them into buff A. And we do the same thing for B. And then we're ready to actually run stuff. Okay, so there's timing stuff already in place, and then a trip counter. Then we set our 4 arguments. So remember that thing, that our vector addition function got arguments A, B, C, and N. Apparently, that's now attached to this object kernel. And here we specify our grid size. So that's 1 and our global grid dimension is 1, so we're just submitting a grid consisting of a single work item. And each work group, that's the local dimension, is also consisting of just a single thing. Then we enqueue in the range kernel. What they mean is, give me a grid, I'll run your kernel on it, right? And the enqueue of that, that's going to make sense in just a little bit. Yeah, question?
What is this set for kernel args? Is that a virtual function called?
So I'll show you what's behind that. In this helper that makes this a little bit less verbose, set for kernel args corresponds to set kernel arg number 0 to your first argument. Set kernel arg number 1 to your second argument. Set kernel arg of 2 to your second argument. And these are just functions in the CL interface. Make sense? Okay, right. So we're running this thing and measuring the time, cleaning up a bunch of stuff, and that's it. Okay, so let's go for it. Huh? Oh, for now we're not reading anything back. Well spotted, though. We'll add that with time. Right. So how many did I do? What do I want to do? Let's do 10 million and 10 trips. Woohoo! Oh wait. What's your reflex when you see that number? Yeah? Yes! Great. Exactly. Physics called and wanted its measurement back. Can't possibly happen, right? So what went wrong? Well, on top of that, we were just talking back to our CPU, right? So, this was not supposed to be that great. Okay. Well, so let's see. Maybe that had something to do with clock frequencies or other nonsense that we saw in the first lecture. So let's see how fast this thing is running. Right now, it's running at 1.6 gigahertz. Let's make it go to as fast as it can go. What was that? Set governor performance. Yes. Okay, did that for all 16 cores. Now it's running at that speed. Okay, but that if anything, that's going to make it faster. Except not quite. It didn't really influence that. Okay, that didn't fix it, but it was good. It was good to do that. Let's do another thing. So I'm gonna actually take you up on your suggestion, and let's also check the answer. That's probably important, right? So okay, how do I check the answer? Where's the answer now? Suppose there is one. Huh? Right, it's over in device memory. So if we want to check it on the host, we have to transfer it back. If you just had to guess, how would you do that? Huh? Okay, and so given that copying 2 was called enqueue write buffer, huh? Say again? Read, yes. So CL enqueue read buffer. So we're just gonna kaploink that down here. So enqueue. Well, since the work is done, conceivably somewhere in that area. I mean, I care about how. Yes, there's. I mean, if you're just transferring data out, doing one thing and transferring it back, then the transfer cost should be included. Whereas if you do a bunch of work on the device and then transfer back, which is obviously the preferred way of doing things, then the transfer cost doesn't matter so much. Valid question. Let's measure after for now. Right. So I'm just gonna read back, and I'm gonna read back C from that buffer, and then I'm gonna go ahead and check if that came out right. So I less than n plus I. If C of I is not equal to 3 times I, then I'm gonna printf that thing was bad, and print the number and abort. Okay, so let's see what we get. Okay, what conclusions are we drawing here? Not only did it go impossibly fast, it also didn't do even the first entry right. So we're obviously misunderstanding something pretty severely. What are we misunderstanding? Huh? No, so right now we're doing a one by one grid. I'm pretty confident that we've got that right? So that's just the simplest thing that the thing can do. What else? What other word have you observed throughout here that we haven't talked much about? Huh? What did you say, Jackie? Kernel? Well, sure. The kernel is doing the work, but it isn't actually. But I mean, at least we didn't get any runtime errors, so we at least talked to it, right? So, Q is a good suggestion. Okay, so let's quickly think about what might be up with this Q business. Well, this is the story. So here's the host, and here's your compute device. And what you do when you say CL in Q something or another is, well, you just dump a bunch of stuff into this queue. And then the device, at some later point, executes that. So remember what we enqueued? We enqueued transfers and we enqueued grid executions, right? So the device actually gets to those at some later point. So based on that information, can you explain the two things that have gone wrong? Yeah?
Sends out instructions, says I'm done, and immediately press feedback again, so that
Right. So well, by the time we get to this checking loop, what have we waited for? Absolutely nothing, right? So the thing just went out and maybe started doing at least the transfer off of the host, but there's no telling how far it got in the computation. And as we saw from the end result, it just didn't finish at all. So okay, what do? Well, we're just gonna wait for everything in that queue to finish. And how do we say that? Well, we say that by CL finish. Yeah? Do I? That's a great question. Should I put the finish before the read or after? Given that the read is also an enqueued operation. As in, I just submit that as work, but it finishes at some undetermined later time. Right? So in order for this to make any sense, the read must have finished. So I have to wait for that too. Make sense? All right. So let's see. Well, let's run it this way. Okay. Well, at least it succeeded. It didn't print bad anything. But it was still a little bit too quick. Huh? Say again?
You have to define all of the
All right. So if you look at where the time is being taken, that's still taken at a point that's completely independent of where we actually wait. And obviously, if we want to time how quickly the device goes, we have to make we have to time only the execution of the actual kernel on the device. Okay. So where do we put where do we also have to wait? Well, we at least want to know that this guy finished, right? Before we take the time. Okay. So let's stick an additional CL finish in there. Okay. Ha. So what do we call 6-ish gigabytes per second? At least not bullshit anymore. But then on the other hand, this is some reasonably beefy 16-core machine that belongs to a friend of mine at Rice University. Thank you very much, by the way. And that only got 6 gigabytes when my wimpy laptop got 12. Oops. Okay. Well, what else are we doing wrong? So that's better, as in we're at least certifiedly doing useful work, correct work. It's just taking a little bit too long. Yeah? Sure. We're gonna get to making stuff more efficient, but there's an actually much more glaring fault here with the timing still. Huh? Well, the dimensions are bad. I'll give you that, but let me fix that second. Let me fix something else first. I have to insert another CL finish. Where? Huh? In the loop in here? As in, do I? Well, no. I mean, the way it is totally fair. I can just submit 10 trips and then it'll do them and tell me when it's done. It's more that other stuff is spilling into my timing from the top, right? There's more enqueued work up top, right? All my writes are also asynchronous. So by the time that I take my starting time, I'm not guaranteed that the writes have finished at all either. But I didn't really care about those. I wanted to just time the calculation. So in order to make that happen, I'll add an extra finish here. That way I'm certain that none of this nonsense from up top spills into my timing. Okay, let's run the thing. All right. Yeah, we won a couple of gigabytes, but nothing stellar. Okay. What else are we doing wrong? Possibly. Well, so somebody said grid sizes. So the way that we've written this code right now, how parallel is it? It totally isn't, right? So the source of the parallelism in OpenCL is this grid. So the bigger the grid, the better. And right now we're just submitting a 1-by-1 grid. So if we look at how busy, whoops. Oh, come on, don't do this to me. Yeah. So, well, my plan was to show you, a little graph of how busy each of the processors is. And you'd see that, this exercise is just a single core. Huh? Oh. Oh, sweet. Okay. Let me try. Yes, you're right. Great. Okay. That one's solved. So let's run it. Right. So there's just a blip on a single processor core, right? So in terms of fantastic, even if I run this longer, right? So let's do 40 trips instead. Yeah, it doesn't even show up properly. Let's do 200 or something. Right. We haven't written the parallel code at all. Not in the slightest. Okay, how do we fix that? Well, let me go back and show you the kernel that we wrote. So that insists on doing everything, right? How do we change that to make it just do, well, maybe one thing? Huh? So okay. Divide's already too, as a hint, already too complicated. So perhaps always the first step in doing something with OpenCL is how am I going to lay out my grid? So in this case, I'm currently sitting on a 1-by-1 grid. What am I going to use instead? If I'm adding a vector of length n, yeah?
You add another input that's like
Yes, I could do some in between thing, right? I could say, like let me create, I don't know, 128 things, and then rewrite this for loop so that it only does whatever it needs to do. I can do something much simpler because the grid is really completely under my control. What's the simplest possible grid I could use for that? Right, just put the entire vector size into the grid. It'll be completely parallel. Okay, how do I change the kernel to make that happen? Hold on, slow down, speak up. Okay. And I say what? Int I equal?
No, that's not.
Huh? An argument.
I'll put it like this.
Okay. What do I pass here as I?
You mean at the probably do everything?
As in, you want me to enqueue n kernels to do all this work when OpenCL already has this nice grid facility, right? Difference it is.
Just calculate I by figuring out the address of the ones who live in the grid.
Okay. How do I do that? These guys. Okay. Got a suggestion? How do I find where I'm sitting in the grid? Local ID. Global ID. Which one is it going to be? Let's take a poll. Global. 4. Yeah. Come on, be a little bit more daring. Okay. So who's for global? Yes, you guys are right. Okay. Yes. So I'll say long I equal get global ID of what? Huh? 0, right? We're going to put everything in one axis. In this case, the x-axis. So let's make that 0. All right, lovely. Now what?
Sorry,
Yeah?
I just want to get off to make the many groups. Each one like in one tree.
Say again?
The goal again will be to like the many trees. One, right? So then if you want like each group work to only go over okay. So that will be the local line.
Right. If I wanted to do something with work groups and local IDs just yet, then I would have to do something. Well, we'll see. Let's ignore the fact that there are work groups for now. Okay. We'll get to that in just a second. All right. So I have my global ID, and that's what my one thing. That's what my one work item is going to do. What else do I need to change in order to make that happen? Huh? Right, I have to tell it what size grid I would like. Okay, so let me do that. What do I change? Yeah, just stick an n right here. And let's run the damn thing. Okay. Make, run. Woohoo. I see all processes revving up. And what are we going to get out of that? Taking a don't tweet, wow. Maybe I'll do fewer trips. How about 20? Okay, that's apparently one of these cases where not all parallelism is good parallelism. What's the problem? Do you remember? So, what are we doing? Huh? Right. So the abstraction. So if you go back and look at our work group size and this LDIM here, that's 1. So what we're doing is saying, hey, you, core number 0, you add these two together. Great. Core number 1, you add these two. Amazingly, we're still getting something like 2 gigabytes out of that. But it's not really the world's most efficient thing, right? Okay, so then how do we fix this? How do we tell each core to do more work? bigger work group, right? That was the thing that controlled how much work went to each individual core. Okay, so what work group size do we pick? What's a nice size? 1024. Okay, we can try that. 1024. Then, okay, you guys believe that this is parallel. Let me get rid of that. Whoops. Okay. What went wrong? It says invalid work group size. Yeah? Well, you're asking if that global ID is still right in the presence of bigger work groups. If you think back to the slides, what was the global ID? Did it care about how stuff was partitioned up in work groups? No, it didn't, right? Oh. Do you have a comment? No? Let me just for clarity, let me pull that slide back up. Right? So the global, what would the global ID of this guy be if the work groups were little 2x2s? It would be exactly the same, right? Just the local ID and the group ID might vary. Yes. Well, I'm actually putting the whole 10 million of the whole vector on axis 0 of the grid. And nobody yelled at me. You know, it kind of went sort of slow, but yes? Right, it does not divide evenly. So if you look at this picture, it seems to be that this global ID along this axis has to divide evenly by the group number, right? Okay, fine. You know, there's an easy fix for that for the moment. What do? We'll simply fix the number of things. So let me do that. 1024 times 1024 times 10. That's the close. Well, there I know that it's a multiple of 1024. So there. Woo! We're winning. Okay, right. So that's how this fits together, right? Now we're giving each core enough work, and it's not starved and just doing, you know, okay, what's the next job I need to do? So, and all of a sudden we're getting at least some relatively decent memory bandwidth out of this thing. Okay, right. Let's see. Okay, now what? Well, this whole thing's supposed to be about GPU programming, right? Let's try GPU. Oops, that was bad. That's also bad. Is that still good? Yeah. Okay. How do we change that? How do we run on the GPU? Right. We up here where it says create context on, so we'll want to run on NVIDIA. And we're actually picky about what we get. We want a 590, pretty please. And run. And, uh-oh. What happened? It was unhappy with us. It says, must specify pragma of OpenCL extension, blah, 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 enabled before using double. Okay, so up to OpenCL 1.1, using doubles was black magic. You had to take this guy here and copy and paste it into your kernel. Okay, I think I can do that. Vec_add.cl, paste, and let me just rerun. Woohoo! That's why we're in this business. All of a sudden, we're not going at 11 gigabytes a second, we're going at 142 gigabytes a second. That was exactly the point of this, right? We're making use of the bandwidth that the device has, and, you know, okay, fine. And threw a little pebble in our way, we cleared that up. Okay. Any questions so far? All perfectly clear? Great. Okay. Now, at some point you might have heard me say, well, you know, the memory, the thing that we just sped up by something like a factor of 10, that's actually the slow bit of the GPU. So it actually can stomach a bunch of more computation on top of that. Really? Okay. Well, let's see. So in addition to doing this stuff here, I'm just going to do some gratuitous extra work. So I'm going to say, okay, double A, no, A is a bad name. AI is A of I, and double BI is B of I. And I'm going to replace this by AI and BI. And then I'm going to say for int I equals 0, I less, no, I've already used I. How about J? J less than 3, plus J. I don't know, I'm just going to screw around some. AI equal 4 times BI plus AI. BI equal 2 times AI. Yeah, I'm not saying this makes sense. But I can run that. Well, okay, our result doesn't come out correct anymore. That's fine. But our memory bandwidth, or you know, like the speed of our computation hasn't really dropped all that much. So in the time that the GPU was waiting for stuff to come back from memory, it could do, well, how many? A bunch. That's something like 4 times 3, about 12 floating point operations, and that's a good ballpark number for everything. For every single thing that you get from memory, you can do about 10-ish floating point operations completely for free, which is worth considering, right? So that it's obvious to see that if you design your algorithm with that in mind, then you can potentially gain a lot just from these floating point operations that you get completely for free. Don't have to pay for them at all. Right. Okay. That's great. Curveball time. Just for grid practice, let's not use a 1024 work group, but instead let's use a 16 by 16 work group, just to get that practiced a little bit. So what do we specify? How are we going to do this? I mean, for a linear vector add, that's I agree, pretty nonsensical thing to want to do, to partition it into little squares of 16 by 16. But just to show that we can, we'll do it. Okay, how? So, fine. I want my first 16 by 16 chunk here. I want my next 16 by 16 chunk here, and the next one after that. And I'll say, okay, you compute the first entry, you the second, you the third, you the 16th, and so on and so forth. Okay, so apparently I'm going to shoot myself a little bit with indexing magic. That's perfectly fine. We're up to the job. How do we do this? So yeah. Okay. So again and slowly. Get group ID along axis 0 probably, right? Times 256. Plus get global ID. Local ID, yes, I like that better. Well, what's the jump? 0 times 16. 1 times 16, yes, I like that. plus get local ID of 0. No, I think that's reasonable. Okay, but in order for this to work out, we have to change the grid size as well, right? So what do we change? Yeah? Okay. LDIM now is going to be 16 by 16. I'll predict you that. Another important thing that we need to change down here is so far we had a 1D grid, and now we're going to do a 2D grid. So that we need to change that so that these get looked at. Okay. Then what's our global size going to look like? Huh? 1 by n. Not quite, right? Because I mean, so what we want is well, how many are there in this direction and how many are there in this direction? Right. So 16 in which direction? Right. So since we did, whoops. Since we did get group ID of 0 times 256, we have to put the other groups along that direction. Okay. So what's the other thing going to be? Is it still n? N over 16, right? Because this is going to still have n square, n little work items, but like overall in the volume. But along this direction, they're going to be 16 per vertical line, so it's n divided by 16. Okay, let's hope and pray. Did I screw something up? Well, okay, let me take all that free flop nonsense back out so that we have some confidence in our answers. Oops. Yep, that did it. And another remark: how big was the drop in terms of performance from the from the more straightforward grid? There wasn't one, right? So that's precisely the point. Or well, it was 4 measly gigaflops. That's round off. Which is fun to say when you know in the back of your head all the CPU had was 11, right? Right. So the key thing is with all this grid stuff, it comes more or less for free because it's done in hardware. So it's a programming level convenience that you can use to organize a program that might prefer a 2D thing, a 2D grid, and the hardware is going to take care of all the funny numbering for you. That's the point of all of that. Okay, great. I agree that that's slightly unrealistic, though. You're not going to do that for just a vector, right? Yes? Oh, so I should ask questions on that. Yes? No? Perhaps? Maybe? Yeah? Right. I was going to get to that next. So that's actually the more realistic question, right? So we ended up with this program, and let me back this out as well. So we had a 1024 by n grid. Let me check that still works. Oh, whoops. Oh, right. I backed out the wrong thing. Put this double nonsense back in. Right. Okay. So that worked for the thing that was a multiple of 1024. But if we go back to our 10 million, it fails us. How are we going to fix that? Well, So I mean, it looks like the device really forces this granularity on us, right? We have to give each core just enough work, right? So it's gonna the grid that we submit is gonna have to come in certain size chunks. Otherwise, this is not gonna be very fast. Well, okay, fine. For adding a vector, that's perfectly reasonable, right? You could say, fine, I'll just have a bunch of zeros at the end that I'm not going to care about, but that's not a really general solution. But it contains a grain of truth. Like, it contains a grain of a recipe. So what could we do? What could we do to the grid if we know our number n is not really divisible by our granularity? That pad with zeros is what he suggested, but let's first just worry about the grid. Yeah.
I know that if might be bad, but you put an if I is
Right. We need an if. We need to check if we're within bounds. So that's step one. So we'll say, okay, what do we say? What's our if?
if I is less than whatever traffic, I guess.
Well, what? Yeah, but how? I mean, what was the length of the vector? N, right? We just passed that as a parameter. So if I less than n, we do that. But that's still not going to solve the whole issue because the program failed way before it even got to that, right? It failed in the submission of the grid. So we'll have to rethink the grid that we submit. Well, right, yeah, that's the third time that suggestion came up. Let's leave our memory alone. So we'll just do something to the grid, right? So the issue is that we have our grid that comes in chunks of 1024, and the last thing is just partially full, as in our n it sits in the middle of a work group. So the easiest thing is, well, why don't we just round our grid size up to the nearest multiple here? And then, so we're executing this stuff over here, too, right? The kernel is going to get executed for these work items, but the first thing they do is check if they're within the length of the vector, and if not, then they don't do any work, right? They just go right. They go right past the if, right? If we're not within bounds, then we return immediately, and that's going to be that. So we don't even need to mess with the memory that we're touching. We're just, adding some extra work at the end where we're not actually doing work just to satisfy the granularity requirement. Okay, so then how do we do this rounding? If you've programmed in C for a while, that becomes second nature. There's a cute trick. So we want to make sure that we want to round up n to the nearest multiple of 1024. So you might think, okay, fine, I'll take n and divide it by 1024, and then multiply it again. Right? So that what has that done? It has rounded down. Okay, what could I do? I could just add 1 to that, and that would sort of do it. There's a better trick. So this, as I've written it, this is going to work. Let me show you. Nope. Whoops. Sorry. I have to add the 1 here after I've divided by 1024. Sorry about that. And that we'll have to get rid of. Do my parentheses match? Yeah, they do. Right, so divide by 1024, add 1 to make sure that we're at least that we're guaranteed to be over, and then multiply by 1024 again. Make and run. Whoop! What you talking about? Anyone see what's wrong? Let me print what I'm submitting. GDim of 0. Wait, what? Apparently I didn't compile because now it ran. Or didn't save or something. Anyhow, our proposed solution works. And yeah?
It's n minus 1 before you get around the possibility that n is actually divisible by
N minus 1. Let me think. That, yes, that works. I'll show a slightly more transparent version of that same trick, I think. Okay, so Marsha, you're shaking your head. What are you disagreeing with?
It's such a low-level detail that the CL compiler cannot just round up numbers. This is what I'm upset about. Here we are trying to figure out when you're n plus 1,023 over 1,024.
Right. In principle, I agree with you. And the underhanded commercial that I could run at this point is, I've told you about this tool Loopy that I'm writing. Guess what? It automates this for you. No, sure, right. So yes, it kind of stinks that we have to do this by hand, but that's the nature of the hardware at this point. The hardware doesn't know how to chop off at the fixed boundary. And like your boundary might be way more complicated than just a simple linear bound, so they've just decided let the program do it itself. It's a hardware complexity thing. It's not perfect, but it makes sense. And the question is, do you want to use the hardware? If so, them's the rules. Right. So, okay. Another comment that you might have here is how much performance have we lost? Not actually a lot. So that's also good. And that despite the fact that we did a whole if and a branch, and I told you branches were bad and all of that. So that's the size of the grain of salt that you need to take that with. So if you messages, you got to do what you got to do. Correct code comes first. Fast code comes second. Right. Okay. Right. So then in this, right, as just came up right now, there's one situation here where we're actually rounding up unnecessarily, right? So if n is already divisible by 1024, then we're actually running one too many workgroups. And there's a simple fix to that. Instead of adding just 1 over here, we'll add 1023 over here. What does that do? So if we're divisible by 1024, then that adds 1023, which gets gone as soon as we divide, and then we multiply back up to exactly the right number. And otherwise, as soon as we need to round up, we actually do round up. Same trick that you wanted to do with a -1, but personally this is more understandable to my brain, so I present it that way. Anyhow, so same story in principle. All right. So and as we show here, it still does the right thing. So let me see. Right. Let me see what makes sense. Okay. Next, let me show you a quick preview of what we'll cover next time. So we'll continue. When we start up next time, we'll go right back to demo. And what we'll look at is something slightly more interesting than trying to add two vectors. The task. Oh, you got a question? Yeah.
You limited yourself to the NVIDIA 500
In this case, yeah.
Is there any negatives to just saying choose all negatives that you have to get more negatives
As in, you want to run on all of them at the same time? It's that. The answer is the same as the answer to Marsha's question. Unfortunately, CL is just not that smart, and so in order to make that plausible, it would actually have to solve a fairly complicated problem, right? Because each of these little GPUs comes with its own memory that sits really close to the chip. That's why it's so damn fast. Right. So if you just submitted work regardless of where stuff sits on these GPUs, then it would have to somehow magically transfer memory, and rather than give you poor and inexplicable performance, it just says can't do it. You can talk to one device at a time, and then it's up to you to come up with higher level stuff to make that a little bit more bearable. Okay. All right. Any more questions? Yes? No? Yeah?
So could you do that manually by going through and coding in, like send this array here, send to this one GPU, send the other array to some other GPU, and do some other whatever?
Absolutely. Right. Yeah, no, that's how, that's the reason why, people build machines like that, because you can keep like all these GPUs firing on all cores, and you've got something that can easily replace a good bunch of CPUs, right, in terms of throughput. So right, obviously. So also here at this point, you see it's a trade-off. By doing this, you make your life more complicated, and that's not if you're inclined now to say, oh, CUDA is going to be better. No, the abstraction is exactly the same. All this group and grid stuff is the same, just because that's how the hardware works, and the transferring in and out is the same as well. So there's no winning there. If you want to use this hardware for something that you need to go fast, then that's the level at which you have to talk to. So obviously you're not going to do this for just about every calculation. It has to be one that's of relatively high value to you, but that's what this whole class is about. You have something that you're waiting on for days, and you want to have it finished in hours, and then it's fair to spend a little bit of effort. That's the idea. Any more questions? Your question answered? You know what? Then instead of me blabbing about what we're going to do next time, let's just finish a couple minutes early, and I'll see you all next week. And do watch for the homework. I'll send a message when it's posted.